Mhm. Good evening, everyone. I'm Jorge Sangrador, and I'm going to talk about one of my topics in my PhD thesis about air quality optical sensor based on 2D lanthanide MOFs composites. First of all, I want to make a brief introduction about metal organic frameworks, or also known as MOFs. These type of materials are a coordinating compound that extends in one, two, or three dimensions and are formed by two main components, one organic ligand and metallic ions. Those metallic ions act as nodes of the network, while the organic linkers act as bridges between those nodes. And these type of compounds can present different of intrinsic properties while you choose wise those components. The most important part is the periodic structure or crystallinity that can let a potential voice that produce porosity, uh, sensing properties, or molecular storage. On the other hand, we can develop tunable synthesis, which means with a wide election of these compounds, we can obtain different on-demand properties like luminescence, magnetism, or conductivity. With all of these properties in the mind, we thought about one of the most harmful problems of our society, the greenhouse effect, the acid rain, and the atmospheric contamination. This led us to the synthesis of an antenna ligand with non-coordinated functional nitrogenated groups that can act as reception center for different pollutant gases. On the other hand, we needed an easy to measure property like the luminescence of two lanthanide metals. In this case, europium with a maximum emission peak at 640 nanometers and terbium with a maximum emission peak at 543 nanometers. After the election of both compounds, we led to the solvothermal synthesis of the materials, dissolving both compounds in dimethyl formamide. Uh, Putting them in high temperatures and several hours to obtain a solvothermal condition, which means we produce autogenous pressure, leading to the crystallization of the material. This material was chemically characterized in collaboration with the ALBA synchrotron, obtaining two-dimensional layers divided with DMF molecules and dinuclear clusters with 3 ligands and 4 DMF per cluster. Also, this material showed 3 different ligand to metal bonding. The first one was a terminal bonding with two oxygens coordinated to the same lanthanide, the bridge bonding with one of the oxygens attached to one lanthanide and the other one to the other of the cluster, and finally a hybrid bonding between those explained before. Once the material was completely structural characterized, we proceed with the luminescence characterization. For this purpose, we dried the crystal, put in the sample holder, and introduced in a hermetic chamber where we put all the gases inside of this material with a stream of inert gas. After that, we excited the sample with a 355 nanometer laser, obtaining the excitation of the antenna ligand, and with an intersystem crossing between the excited triple state of the ligand, we produce the luminescence of the europium and the terbium, obtaining a similar spectra as the shown before with the 640 nanometers maximum of the europium and the 543 nanometer maximum of the terbium. After this photochemical characterization, we proceed to the sensing gas pollutant measurements. we introduce the samples in the same vacuum chamber and purge it with 15 minutes of inner gas and cycle with 5 minutes of pollutant and inner gas at room temperature, obtaining this type of results where we can see that the maximum emission of the lanthanide suffers a modification in the emission intensity of its luminescence while the pollutant is inside the chamber. This led to three different behaviors with the europium. As we can see, the CO2 produces an enhancement of the luminescence in the maximum peak, about 20%, while the NO2 and SO2 doesn't seem to produce any modification in this luminescence. On the other hand, we had the terbium measurements, where the CO2 produces a similar behavior than the europium with an enhancement about 20%, but in the case of NO2 and SO2, the behavior is completely opposite. These gases produce a decrease in about 20% in the maximum luminescence, so we thought about the possibility to develop a mixed material with europium and terbium emissions and use the europium as a blank of the measurements. But we tried the mixed crystalline synthesis, but without good results because the europium was the only one metal that emits in this material. So we proceed to make thin layer composites where we disperse these crystals in a polymeric matrix, in this case polydimethyl siloxane, and obtaining a material with a similar luminescence behavior that the sun in the bulk material. After that, we proceed to obtain a new and completely novel multi-lanthanide emissive material, where we have the emission of the two metals at the same time, so we can measure both emission peaks as the gas is passing through the MOFs. In this case, we obtained that the CO2 doesn't seem to produce any modification, so we discarded this gas for this type of sensor. But in the case of NO2 and SO2, we obtain the same behavior as the zone before, where the terbium decreases its luminescence in about 20%, and the SO2 shows a decrease in about 22-23%. This led to the possibility to obtain a radiometric sensor where we can use these materials as for different concentration, in which we can see that the luminescence of the terbium decreases gradually as the concentration is bigger for NO2 and SO2, allowing us to develop this calibration where we obtain the limit of detection for both materials in about 5 ppm of concentration. Results that are lower than the given by perjudicial for by the Spanish government. Finally, we have demonstrated that it's possible to synthesize a novel lanthanide-based MOF using ligand with no coordination functional group as recognition center for different pollutant and atmospheric gases with different metallic centers that present different cloying states, which implies a different luminescence emission and different behaviors as the pollutant passes through the material. Finally, it's been demonstrated that it's possible to disperse these materials in a polymeric matrix, obtaining a composite with multi-lanthanide emission properties similar as the bulk. And this material can act as a radiometric sensor for the two different atmospheric pollutants with a low limit of detection for SO2 and NO2. I would like to thank all of you for your attention, my group, and my teach director, Jorge Sánchez Costa and Juan Cabanillas. Hemos intentado otros contaminantes, pero el problema es sobre todo introducirlos en el sistema que tenemos de la cámara de gases por la agresividad de otros contaminantes. De hecho, tuvimos que reducir mucho la concentración de SO2 para no afectar al sistema de gases que tenemos en el laboratorio. No, no tenemos la capacidad actualmente de introducir monóxido de carbono en el laboratorio. Por seguridad, más que nada, necesitaríamos tener diferentes permisos a los que tenemos con estos gases, porque de hecho los gases que tenemos los tenemos que hacer en bajas concentraciones, sobre todo. Sí, de seguridad. Y es posible que el monóxido de carbono genere reacciones con los grupos laterales que tenemos dentro del MOF. Otra vez tenemos esto. Pues, este- no sé cómo funciona. Ah, este no, es el otro. Ah, es este de aquí. Sí, sí. El caso es que nosotros hemos usado sobre todo el europio como blanco de calibrado interno dentro del material, porque aseguramos que su luminiscencia es constante a lo largo de toda la medida. Entonces podemos asegurar que ese sistema es inerte y podemos usarlo como un banco de calibrado de que no estamos modificando cualquier otra cosa dentro del sistema. Sí, en el caso del material cristalino puro sí queda señal, pero lo que hemos visto es que el polimetilsiloxano es completamente inerte al CO2, es impermeable al CO2 porque no puede entrar a través de los poros. Por tanto, nos permite descartar como posible interferente el CO2 solo usando este polímero.